So we'll try to do what we can for the book, but the PowerPoints are available for you online, and they should be available as 3 slides per page. So if you wanted to take notes that way, that's a good way to take notes. So what we're going to do now, of course, is just get an introduction to this. And we're going to deal with numbering systems and just get an introduction into digital. Numbering system in codes. This will be chapter 1 in the book, but like I said, this is something we can teach without the book. We'll want to, so this is the pretest. What's the difference between analog and digital? Anybody know?
Well, it kind of varies in terms of digital, one or the other.
Yeah, it's either one or other. Okay. What's a numbering system? That's the way we count and the way we do math, right? The numbering systems. Base of a numbering system. Anybody know what a base is? Base is basically it's what we use to calculate the weights, but technically base gives us the number of combinations a single digit can have. So if we have what we call a base 10 system, it means a single digit can have 10 combinations, and those 10 combinations would be 0 through 9. A binary is a base 2, so it means it can have 2 combinations. Most of our numbering systems start off with the digits that we use in the decimal numbering system. So a binary numbering system has two. It's a base 2 system, so it's got only 2 combinations, which would be what? 0 and 1. Hexadecimal is base 16, so it's got 16 combinations. So we start off 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go A, B, C, D, E, F. So we have to pick up letters. Octal numbering system is a base 8 numbering system. It goes 0, 1, 2, 3, 4, 5, 6, 7. So there's 8 combinations that a digit can have. And then we combine digits to make what we call numbers, right? You understand? A number can be a 1 digit up to, millions of them if you want to. The number systems we're going to look for is decimal, which is a base what? 10. Binary is a base 2. Octal is a base 8. Hexadecimal, hex is 6, decimal is 10, so hexadecimal is base 16. These are the number systems you'll run into in any digital type of technology. Anybody know what a bit, a nibble, a byte, and a word is? Huh? Bit, nibble, byte, or word? Well, we'll learn that. Huh? So we'll learn that. And then kilo, mega, and giga. We use those terms a lot. They do not mean the same thing as they do in the base 10 numbering system. So basically, digital is a base 2 numbering system. While we learn but when we start dealing with 2 combinations, and we'll look at that. In fact, we'll look at that just a hair here in a second, and just give you a reason why we learn all these different number systems, even though digital is basically a binary system. Huh? I don't know, you must not have paid attention. The book they have in the bookstore is the wrong book.
Yeah.
They have us down for solid state. They do have it?
Yeah.
Yeah. This is the book right here. Okay, but on the shelf for our book, they have solid state, and they got it on their records that it's that book. But this is the book for the class right here.
No,
Everybody
he
see?
looked at the wrong one. Under this one, it's written ETC127,
Okay.
and your name is there.
Okay.
On it. But he didn't have it on the shelf. He had it in the back, so he took it out.
Okay, thank you. I'm glad to hear that.
Yeah.
So this is the textbook, and it's on the syllabus. Thank you, Karim. I'm glad you went up there now.
Yeah.
Huh? Yeah, they're not cheap. Textbooks are not. Technical textbooks are not cheap, guys. And I would be very upset if I got into a class they didn't use the book either. So,
You can't use the code. I
The
got brand new
only
code.
difference in this one, you have posted the edition 6, this
That's-
is edition 9.
Okay, it's just the
Same, you
same
upgraded
one.
one, that's what
Yep,
you say, like.
that's fine. So this would be an example of a binary number. And you can see it becomes very cumbersome, right? Okay. And what I'm going to do, and if I was trying to give this out to you, and I was going to say 1010 1, of course 10 10 10 11 10 10 11 1011, how many would get that right? Nobody, right? You understand? But if I could break it down into a shorter groups, so notice what I'm doing is I'm going to split this into groups of 4s. And I would just say 5, 5, 5, and then I would just say D, 5, 7. And I do it that fast, 5, 5, 5, D, 5, 7. Just about everybody would be able to write that down. So what we do with these other numbering systems is a way that we can represent extremely large binary numbers. So a lot of computers, instead of you dealing with entering binary numbers in binary, they let you enter it in another base. So you know, it amazes me that a lot of people learn all these numbering systems and they don't know why we do it. Why do we learn hexadecimal? What advantage is hexadecimal over binary and that kind of stuff? So binary numbers are very, once we get past 2 or 3 bits, which is a single binary digit, once we get past so many bits, it gets very confusing for us on humans, right? Or just following and keeping up. So this is why we're going to learn. So this is why we're going to learn all these different number systems, because these are the numbering systems that most of your machines use. As an example, even in Windows, if you want to go and look at the layout, so this is a binary machine. So, but we have the ability to look at a lot of information that a lot of people don't know. So down here under System, I can actually go and look at I might figure out where to get to it on here. It's not device, it's maybe System. I don't want to go to device manager. I'll have to find it in here. Let me this is a Windows XP machine that I'm logging into. And I know where it's at in here. So when we look at the information on the computer about the resources that's assigned to the computer, getting more.
Yeah.
I'll come back and show you that. I don't want to sit up here all day. This is digital. So when we're talking about digital, we're looking at terms like on, off, 0, 1, yes, no, true, false. Analog is continuously varying. And what people don't understand is, you know, you say, okay, which one of these is most accurate? Huh? Analog. So analog has the ability to deal with infinity. we can act, so it's like, you know, the sun, when the sun comes up in the morning, it don't come up bright, it comes up and gradually goes. Well, how many light combinations is there from midnight all the way up into the day? Well, there's literally an infinite number of light combinations because it's analog. So analog, representing analog information is a heck of a lot more accurate than digital information. But the problem is it's so hard to deal with. It's so hard to transmit. It's so hard to store. We can't store digital analog information and use it later. We can't compress analog information. We can't run it through an algorithm or a program and make it smaller for sending it, and then when we get it on the other side, we run it through an algorithm again and do what? And expand it back out. So digital data can be compressed, it can be added, it can be subtracted. The circuitry that handles digital is so much easier to design and cheaper to design than trying to deal with analog. So these are two watches. The one on the left is analog and the one on the right is digital. We have people now that can't even read one of these guys. They can't read an analog watch. I got a niece of mine that if you put one of these watches in front of her, she'd be totally lost. She'd be off all the time because she has no idea how to read a analog watch because they don't teach that anymore. You know, when I was in elementary school, we learned how to tell time on an analog watch. Now our watches do they tell us the time, the date, and a bunch of other stuff. We represent analog data all different ways, you know, CDs, DVDs, television now, it used to be analog, but now TV is digital. Your TV has to be able to receive that information because what they're doing now is they're compressing that information to increase what we call the bandwidth. The bandwidth is the range of frequencies that a media can pass. Well, if you can compress the information and send it, then you can get more stuff within that bandwidth, right? Does that make sense? So our digital TVs are digital now. It wasn't that we could do high resolution with analog. It's just that to send high resolution analog would take so much bandwidth to send that information to do that. So we do a lot of digital. Most of your actual audio, so it's real strange. Our CDs are digital, but our speakers are analog. So that means that we have to have a process where we go through some device inside our DVD player or our stereos to do what? To send it out of speaker. So we have what we call A to D and analog to digital converters. So these are some digital devices hopefully y'all are familiar with. We have digital cameras now. I still got a nice Yashica camera that snaps with film. I never use it anymore, but I show it. Digital cameras are so neat. You know, they save pictures in a compressed format. You know, I think my camera has like a 4 gigabyte memory card on it, and I've never ever even come close to filling that up because they're all what? They're all compressed. The images are compressed. The old days, you took picture on film. You know, you had 32, the big rolls of 32, the small rolls of 24. And then what you do after you finish the roll? Take it someplace and have it develop. And you didn't know what the pictures actually looked back until they what? Got them back. Right. Yeah. Now they're on your phone. If you don't like the way the picture turns out, you just do what? You just delete it. So and they're compressed. So you know you got phones now that holds. Like I said, my Nikon camera, I've never filled that thing. I mean, I have 400 or 500 pictures on there before I download. These are analog devices. Of course, we still have analog clocks around. A lot of your motors, especially motors that you control the speed of, speed control motors. These are analog. Microphones are analog. The sun is what? Analog. Speed is what? Analog. The universe is analog, right? Understand? Your body is analog. Temperature is analog. So we're living in an analog world with digital, and so we've got these. We're going to look at. We've got devices called analog to digital converters. So I've got a computer right here that processes digital information. But if I was to hook up a meter to it, if I had an interface board that I could hook up a meter, the information I'm measuring is going to be analog, right? So now we have these meters right here. So the meter is digital, but what it measures is what? Analog. So there's a circuit in here, we called it an analog to digital converter, right? And then of course we have, and then if I got to communicate, if a digital device has got to communicate with an analog world, we have what we call digital analog converters, which hopefully we'll get time. So that analog, we live in an analog universe, but the problem with analog, and analog is a heck of a lot more, has the ability to be a heck of a lot more accurate, but it's almost impossible to process. I mean, it's almost impossible to store. When you come up with circuits that would do math with analog quantities, they're extremely complex. You know, the circuits that does math with binary numbers is very, very simple as far as circuitry goes. So it gives them the ability to put all these math circuits and all these things inside an integrated circuit we call a microprocessor now that does all this math and stuff. But those things are not analog. Those are what? Those are digital or binary devices. So everything you see going on is ones and zeros. So everything displayed up here is nothing but analog. So we turn little dots on. We call them triads. So a triad is a group of 3 colors, usually red, green, and blue. And then we combine triads into little squares we call pixels. Y'all probably heard of that term, picture elements. And we make the picture elements real small or make them real big. And the smaller they are, the more space they take up. The bigger they are, the less space they take up, the grainier they are. So this is what we deal with. So all our computers, now our cell phones are digital. Used to, cell phones were analog, and you could take a police scanner, and very few modifications, you could pick up cell phones and tap into people's cell phones, and it wasn't against the law either, because anything that goes through the air is free. So if you have the ability to intercept communications going through the air, so we had people all kind of problems then, right? You understand? But now they're digital, and what can they do now? They can do what they call encryption. So they can send the code out that is not actually the information. So we encrypt it when we send it, and then what we do. And it's on the fly encryption too. Some of the encryptions they use now is just unbelievable how secure they are. It's passwords that's not secure. That even happens with our email. We'll get an email every once in a while. They'll get somebody's email address, and they'll send them an email saying, you know, you need to verify your email address, click on this, and when you do that, it downloads, it gives that company our whole email list. And you can tell when that happens, we'll start getting this junk mail from all these companies all over the place. And they'll come up and they'll fuss at us about that. And these are people that are supposed to have a lot of education. They ought to take our computers away from some of these people here. What we're going to do first, and like I said, this is in the book, but we can do this without the book. This is pretty. Base 10 we have no problem with because this is a number system we already understand. So what does the base mean? It means every digit has what? 10 possible combinations. And then we use those digits to create numbers. A number is a group of one or more digit. That's what a number is, right? So I can come down and I can write this down. And we're so used to this that we sometimes we lose sight of what this actually means. Now what we'll do in this class is I'm going to subscript the base, because this would be a legal number right here in 2 bases that we know of. It would be a legal number in base 10 and base 16. And the weights are completely different. So what we don't understand is that this is what we call a weighted numbering system, which means each digit holds a weight to the overall value of the number, right? We refer to the number on this digit furthest to the right, no matter what it is. We call this the least significant digit. And this guy over here, we call this the what? This is called the most significant. The least significant digit holds the least weight to the overall weight of the number. So if I was getting paid and my employer jipped me here, I wouldn't go in with a gun, right? Over here, I would be very upset, okay, because that holds more weight than I made. The weighting factors are powers of tens. Now, every base works this way, but we don't learn it this way. They don't teach it this way. We learn we call this units, we call this what? tens, hundreds, thousands, 10,000. That's the way we learned in school. The actual way it goes, every numbering system, the weight of the number is always the base raised to some power. So this right here would be 10, and the first digit is raised to the 0 power. This digit holds a weight of 10 raised to the first. This holds a weight of 10 raised to the second. This would be 10 to the third. Next one will be what? 10 to the fourth, 10 to the fifth. The radix point, which is the true name of the point that separates the whole number from the fraction, normally we move it over to the base. So most people call this the decimal point. So when we move on this side, it holds the weight of the base, but we raise it to the negative power. So this would be 10 to the minus first, 10 to the minus second, 10 to the minus third. And then we would keep going till we ran into infinity, right? No matter how far it goes over, the number on the right is always the least significant digit. The number on the left is always the most significant. So to do this, what we would do, so the 7 would actually hold the weight of a 7 times 10 to the third. And then we'd put a plus, then it would be 6 times 10 squared, right? Plus 8 times 10 to the first, plus 9, plus 9. Any number raised to the 0 power is 1. Yeah. But this actually be 10 to the minus 0. And then this would be plus, and we'd keep going, right? Now this looks nice, and we can tell, but if I wanted to actually get the weight of the 7, then I would have to know what 10 to the third is equal to. So that would actually be, what's 10 to the third? Huh? No, but we're doing this right now. So I say the 7. Yeah, so this is this number right here, right? Everybody okay? And then I can multiply this out, and this would tell me that the 7 actually holds a weight of what? 7,000. And then I could say a plus 6, and then times what? That would be 100, right? So that would hold a weight of what? 600. And then this would be plus 8 times 10. Any number raised to the first power is itself. So that's going to be 80. And then 9. And then when I add all these together, I should come up and get that weight right there. So this is true for every weighted numbering system. So every digit holds a weight of that digit times the base raised to some power. I don't care if it's base 8, base 16. So this is the way what we call weighted number systems work. Are we okay? So that's what this weighting factor of 10 means. So it's always the what? The base raised to some power. Everybody okay? We call this positional notation. So writing the number down in that aspect. So what would it be like if I had 8, 3, 7, 4, 5? If we wrote that using positional notation, what would this be? So this would be 10 to the what? 0, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth. So this would be 8 times what? 10 to the fourth. And then what we would do, we would continue on. And we refer to this as what? Positional notation. Normally what they'll do is they'll put a parentheses around this, and they'll put a plus, which tells you to do that first. And then you would come up here and you'd say 3 times 10 to the third plus 4 times 10 to the first. Oh, 7. I left that one. Go on. I changed color. How's it going? What's your name? Okay. Here's the 3. This is no big deal. We understand the decimal number system. What we're doing is going back and doing this so we'll understand the other bases. So this is not anything you're going to have to memorize. You're not going to do any positional notations for decimal number systems, and we're going to do very little positional notations for our other bases. We're going to learn some of those shorthand methods to come in and figure this out, right? But this is truly the way the system actually works. So this is the number written. This is in something we call positional notation, and then we would take this and to figure out the actual true weight. Technically, we would take this and multiply it by 10,000, right? And then that would tell us what the weight of that number was. And what we're doing on this is just going into the decimal number system, and we're going to take this, and I can apply this technique to any number system. One of the things we had to do when we was in college was make up a base 36. So we had to make it up. And of course, it was basically just taking the first 10 digits that are capable on the decimal number system and just using the rest of the alphabet to represent your other letters. But you could literally make up any base you wanted to, as long as you came up with symbols to represent each combination. So 8 is actually a symbol. And there was no such thing as an 8, and if somebody came up with a symbol that says, okay, this is the symbol for what? For an 8. So basically, we have 10 symbols available to us that's used by the decimal number system, and most number systems start off with those symbols. But once you run out of 10 symbols, then what do? Well, you can make up your own dang symbols if you wanted to, and it might come up to be a standard, you know. So hexadecimal, they use A, B, C, D, and F to represent 10, 11, 12, 13, 14, and 15. Those are the symbols that are standard for that base. So now if you use hexadecimal and you're going to do the standard, you're going to have to use those symbols. But if they say, okay, I want to make a base 12, well, there's no such thing as a base 12, but so you would have to come up with some more symbols, right? You don't have to use those letters. And if it got adopted, that's fine. Then now you might have your name on the name of a bug or something, right? But that's what we're talking about here. So normally, if we understand base 10, then we'll be able to move into these other bases, but we need to know the technical aspect of base 10 to understand those other ones. So now we can start making shortcuts with those other ones like we do with the base. And normally, any other base, we're going to have to figure out how to get this back to base 10. Because why? Because I understand base 10. I can look at a base 10 number and I know what it's equal to. So normally you come up here and you throw a number down like this, and it's base 2, and then I come down and write a number like this, and most people want to say that number right there is bigger because it has more digits. Well, it's not. It's actually a lot smaller. It's just that the weight of each number is so small it takes more digits to represent the numbers. So normally what we would do is somehow we're going to have to figure out how to get this binary number back into what? Into decimal, besides using a calculator. We have scientific calculators that'll do us now, but I'm a firm believer that if you don't know how to do it longhand, you don't need to be using a calculator. Y'all understand that? Because if you can do it longhand, you understand what the calculator is doing. So yeah, we can go between bases real easy. If you got Windows and switch it over to scientific. No, the new version of Windows have 3 versions. They have a scientific, and then they have a programmer's calculator that'll convert between all these bases for you. But you'll find out after you learn some techniques, a lot of these numbers you can do in your head. And that's really impressive sometimes. So let's look at base 2. This is the guy. This is the guy that we use, that we learn all these numbering systems, all these other numbering systems besides decimal. This is the guy that the computer actually uses. So when you get into programmable logic controllers, computer uses binary. Your cell phone is a digital device. It uses what? It uses binary. But we're going to have to represent this in other bases because binary becomes so cumbersome. So we only have 2 digits available to us in binary, and these are called bits, by the way. So in binary, we don't even call them digits. The individual digits in a binary number system we refer to as a bit, BIT. So the only two-bit combinations we have for our digits is 0 and 1. So everything we do in binary has to be represented somehow with 0 and 1s. But what can the 0 and 1 be? Well, the 0 and 1 could be a number that I write down on a piece of paper, or I could use voltage levels, right, to represent binary. So a voltage level could represent a 1, and a 0, and a ground could represent a what? 0. So now we can represent these very easily using electricity instead of using analog. It's real hard to do that, right? You understand? The analogy we use is, you know, even if I went to the decimal numbering system and I had a flashlight and the flashlight had 10 switches on it and I put 10 different brightnesses on it and sent you across over there to the library and sat over here and was trying to send you numbers with that flashlight, how could you get the numbers right? But if I was turning the light on and off, it's trying to send you information with turning the light on or off, how far could you get away from me and still be able to send you information? Navy still uses the technique. That's binary. They still have the dang lights on those ships that they can do what? That they can communicate from ship to ship so they don't have to send that information over the air. Because if it goes over the air, what? Yeah, if they can pick it up and decode it, then by George, they got your information. But if they're not in line of sight, so those things have lenses and they point them right at those people and shoot those lights at them, right? And how far can those ships be apart? Well, as long as they can see each other, if they're not over the horizon, they can send information to each other. So the weighting factor of binaries too. So our binary numbers is like this. So if you ever see this, you know it's not what? It can't be binary. But just because it has all ones and zeros, this could be a lot of different bases, guy. This could be base 2, it could be base 3, it could be base 8, it could be base 16. So what I try to do is I'll either specify what numbering system it is, or I'll subscript it so you'll know exactly what it is. So this is binary. Is this a big number or is it a little number? Let's knock some of these off so we'll make it shorter. Well, our mentality dealing with decimal, we think this is a big number, but this is not. This is a relatively small number. But this holds the weight of the base. This is 2 to the what? 0. This holds the weight of 2 to the first. This holds the weight of 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh, eighth, ninth. If I put a binary point there, then over here, this would be ones and zeros. This would be 2 to the minus 1, 2 to the minus 2, 2 to the minus 3. I need to make my digits bigger. Now, what does that mean to us? I don't mean anything. Because I'm seeing this in my head, I'm seeing this as what? Decimal, but it's not. So what we need to do, of course, is we need to get this over to a decimal number. So what we're going to do, let's not deal with the fraction right now, let's deal with the whole numbers, is what we're going to do is we're going to figure out what the decimal equivalents of these powers of 2s are. So I know any number raised to the 0 power is equal to what? 1. And you'll ask a lot of people that, 2 to the 0, and most people will say 0. 2 raised to the first is itself, what's that? 2. 2 squared is 2 times 2, what would that be, what? 4. 2 to the third is 2 times 2 times 2, so that's 2 times 2 is 4 times 2 is 8. Can you see? So 2 to the fourth would be 16, right? 2 to the fifth would be 32. So what we do every time we go up to another power, we just double the previous power. That's all you have to do, double the previous power. Now what I'm going to do is, this is not right, but what we're going to do is we're going to take this same number and I'm going to spread it out. And then what I'm going to do, instead of writing the power of 2, I'm going to write down the decimal equivalent of the power of 2. So I'm up here, I'm going to write down 1, 2, 4, 8, 16, 32, 64. Now, a while ago, when we had the decimal number system, we took that right there and we multiply it by that, right? Well, this is pretty easy because any number times 1 is what? that number, any number times 0 is what? 0. So all I'm going to do is I'm not going to worry about these digits that's got zeros in them. I'm going to come down here and I'm going to add 64. What would be my next one? 16, 4, 2, and 1. I add those together and that's going to give me these are decimal numbers. I'm adding decimal numbers, so I'm going to get a decimal answer. What is this, guys? $87? Okay. So this is 80, 87. This is decimal. Is that a true statement? 87 equals that number. Sure. It's just that you're looking at the same number in two different bases. So going from binary to decimal is pretty easy. All you got to do is be able to multiply by 2 real fast. 1, 2, 4, 8, 16, 32, 64. What would be next one be? 128, 256, 512, 1024, 2048, 4096, right? 8192, 16,164, right? 32,000, right? So y'all can see I've done this a lot. So it's once you learn them though, you get the you get it right. And I could do this in hex, and I could have done the number real fast, and I'll show you all those little tricks too. You see how fast I came up with that answer, right? Because I'm looking at it in another base, and it's basically learning. And on your other bases, it's basically learning multiplication tables, and that's something y'all had to do in school, right? Y'all remember multiplication tables? Learn those flashcards. And why did you learn multiplication tables? Because what is multiplication? It's addition. So instead of me adding 5 plus 5 plus 5 plus 5, I learned that I memorized that 5 times 5 is what? 25. But all multiplication is addition. When microprocessors first come out, they could not multiply and they could not divide. All they could do is add and subtract. So the first microprocessors I got in, the only thing they could do is add and subtract. So what did we have to do? We had to write programs to make it do what? Multiply. Now, of course, they can do all kind of math now, but in the old days, that was fun. And that was when you learn how to do the binary language programming for the computer, that was some of the basic tasks, is learn how to write a program to do multiplication, learn how to write a program that does division, learn how to develop a program that does roots, right? Square roots and squares and that kind of stuff. And it was very, very interesting. And that's when you really learn the math, how it works, trying to figure out how to write those that we punch into a calculator now, that somebody else wrote a program to do that math, which is pretty neat. Yeah.
Why did you say
What we do is this number right here is and it's just a technique that I've got into. But that combination of digits is legal in multiple bases. So what I'll try to do, this is a subscript that I use to identify the base. This number right here would be a legal number in decimal, right? You understand? So I could just as well come up here and say, okay, what would be that decimal way to that number? And that would be a big number, right? You'd say that would be 1,010,000, right? Or it could be what? It could be a legal number in binary, or it could be a legal number in hexadecimal, or it could be a legal number in octal. So I've got all these bases, and if I throw a number up here, I need to identify what base that belongs to. So it's just something that I'm used to. Putting that 10 down there, it just means this is a base 10 number, a decimal number. This is a what? This is base 2. So it's just a way of identifying what that number is. Are we okay? Okay, so let me, I'll discard this. I didn't want to exit that, Rich. That's what I was looking for. I didn't see it. So let's do a number. So y'all do this number right here. So let's keep them around 8 bits. Now this is what base? Base 2, so that's all it means. I'm telling you that's the base 2 number. And what we're trying to do is trying to get the decimal equivalent of this. By the way, I'll run this off for you in a second. We'll give y'all out a chart that shows y'all these powers of 2. So all the way up, I think, to 2 to, I think it goes all the way up to 2 to 32nd. Anybody got it? Got it? I want the weight of the number in decimal. What's that? What'd you say, Kyle? Okay, so this is one answer. Just because you don't get it, it don't hurt you on this, right? Huh? By the way, this bit right here, it's just like in a decimal number system. The least significant digit of a number determines if the number is what we call an even number or an odd number. Everybody understand that? In binary, the only way this could be an odd number if this is 1. If this is 0, your answer should be even. So that means if you take an odd binary number, y'all understand what I'm saying? So this right here, this bit right here is the only digit that determines whether the number is even or odd. So I could come down and I could put 8, I could put 6, I could put 4, and I put 3, that's an odd number. Even though these are all even digits, this digit right here determines if the number is what? Even or odd. In binary, it's a lot easier because you don't have to learn that 1, 3, 5, those are odd numbers. If it's got a 1 in it, it's an odd binary number. If it's got a 0 in it, it's an even number. An even number in any base had better be an even number in any base. So notice this answer has a chance of being right. It doesn't mean it is right. It has a chance of being right because it's an odd binary number, and I should expect an odd decimal number, right? You understand that? If I have an even binary number, I should expect an even decimal number.
So he's saying that, well, 2.
It's not going to ever be a 2. It's
0.
If it's a 0, my decimal is an even number. If it's a 1, it's an odd number. Because that's the only odd number in the power of 2s. It goes 1, right? 2, 4, 8. If you add an even number plus an even number, you'll always get a what? In fact, if you add an odd number plus an odd number, you'll get a what? Huh? Huh? Yeah, if you add an odd number plus an odd number, you'll get an even number. The only way you ever get an odd number if you take an even number and add it to a what? An odd number. But here we're just going that way. So here the only odd number we got in this whole group right here is that bit right there. All these are even numbers. If I add all these, so the only way we'll get an odd number if this one is if that bit is set, right? You understand what set means? What set means it's a 1. Or if it's cleared, what the term cleared mean? Means it's a 0. So Kyle's answer has the ability, it could be right, it don't mean it's right, but it could be right because it's an odd binary number and he came up with an odd decimal number. But if I come over here and have an odd binary number and my math comes up and gives me an even answer, I know it's what? I know it's wrong. Anybody get anything any different? Anybody want to see it work? So let's go back and do this. So what I'm going to do is I'm going to come up here and write this across the top. So 1, 2, 4, 8, 16, 32, 64, 128. So if you answered 70 something, you know you're wrong because I know I got at least a 128 in here, right? Everybody, huh? 254. Can't be two. I know that this number right here is 255. So I know it can't be 254 because it's got a bunch of zeros in there. But let's do it. So this would be 128 plus what? Plus 8 plus 4 plus 1. So y'all see where y'all went wrong. You didn't get the same answer. See where y'all went wrong? Real easy to skip over a power of 2. That's why I write them up. Yeah, it's real easy to skip over a power of 2. So we added this one. We skipped over this one because it's a what? 0. Skipped over this one because it's a what? 0. Skipped over this one because it's a what? 0. Added this one. Added that one. So we only add the equivalent decimal numbers that have 1s in the bit position. We do not add the ones that have what? 0s. Because that's the positional notation. So this right here is going to be 1 times 2 raised to the what? So this is 0, 1, 2, 3, 4, 5, 6, 7. So this guy here holds a weight of 2 raised to the 7th power. But that's 1, and this is going to give us a number, right? You understand? This guy right here holds a weight of 0 times 2 to the 6th. Well, what's 0 times any number? How much weight does a 0 hold toward the weight of a number? Nothing. So that's why when we go from binary to decimal, we just skip over the bits that have what in? 0. And only add the decimal weights of the bits that have what? 1s. Because if I took 0 times 64, what's 0 times 64? 0. So y'all understand that? I don't know why I didn't choose a raise up last time. It's like, that was one of my options. So if y'all take PLCs, they'll go over this in PLCs too, so y'all be way ahead of the game. You'll get it several times. Because we live in a digital world. We live in an analog world, but a lot of our technology is digital now.
15.
So this is one answer. Anybody get anything different? And you wouldn't believe what hassle it is for these computers to do this for us. So our computers do this for us, but when it's actually dealing with this over here, right? You understand? 215. Anybody want to see it work? Yes, no? We okay? Y'all go ahead and take a 2-minute break. I'm going to run this sheet off for y'all.
So what do you call this here? Binary.
Base 2 binary. It's called base 2, but the name. So decimal. We got decimal, right, and we got base 10. Those are saying the same thing, which is the decimal number system. So all your number systems also have names.
Putting down the numbers, then you put it on the below chain of 2. That's like decimal.
Yeah, and that's what we're doing. So what we're doing is we're taking a shortcut. Y'all understand that? The actual technique would be to go through position location, but we're taking a shortcut instead of going through position location. What we're doing is writing so this guy right here does not technically hold the weight of 1. It holds the weight of 2 to the 0. Technically, this holds the weight of 2 to 1. Y'all understand that? But what we're doing is we're bypassing some steps and go ahead and writing the decimal equivalent of the power of 2. And of course, it's real easy because all we do now is have to do what? Just start off with 1 and do what? Fractions get a little more touchy. We'll look at fractions when y'all get back off the day. So I just start off with 1 and go what? 2, 4, 8, 16, 32, 64, 128. And once you get into the flow of this, and after a while, if you deal with it long enough, you will learn the powers of 2s, and you'll learn them out pretty far. So what would be next? 256. Then I'll double that and get what? 512. These are pretty standard numbers, and then what would we come up? 1024. By the way, this is 1K. In binary, it's 1K. So in binary, 2 to the 10th is 1K. So people don't understand that when you start talking about gigs of memory and stuff like that. This is a base 2K. Now in base 10, a K is 10 to the 3rd. In base 2, a K is 2 to the 10th. So a K in binary. Yeah. So what would a meg be? To the 20th. Yeah, to the 20th. So basically we jump in 10s on binary. Are we okay? 1024. So that gets people confused, and people don't understand why you go out and buy a certain size device and you actually look at the memory. It usually shows more than you think you got, because that 8 gig is not, it's 8 gig in binary, not 8 gig in what? In decimal. So y'all go ahead and take a break. Let me run this sheet off for you.
So in hexadecimal, would that be E7? In hex, would that be E7? Yeah, I broke it down. That's what you do earlier. I had to do that in class a long time ago.
Yeah, what we'll do on that though is you learn. Yeah, you can use flip cards, and what you do is you memorize patterns, 4-bit patterns for each letter. Let me run this off for y'all. So I'm glad the book is over there. They just had it in the wrong place.
We had to use, you didn't have to use base 32. It wasn't used for anything.
What's that?
We didn't learn base 32. It wasn't used in anything.
Well, what we learned by different weird bases was that it's just for you to learn the technique of setting up a base, and it gives you a real understanding. If you set up your own base, it gives you a real understanding of the bases that we do use.
When you get to really long bases, you go from capital to lowercase, don't you?
So y'all should be able to take this out without any problem. Y'all think I have any problem with this? Anybody want to work anymore or work another one or anything like that? Are we okay? Let's jump over to the fraction side. So we'll take a smaller number. We'll deal with a smaller number. As soon as I figure out how to make this thing right. There we go. Here's where we can represent any whole decimal number in binary. We have big problems with representing fractions, because fractions tens move in tenths, right? You understand? These guys here moves in halves, which gives us a real problem. But this right here would hold a weight of 1, 2, 4, 8, right? Well, what this guy here, this is 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4. Now, basically what you do over here is when we get on the fraction side, it's 1 over. Right, you understand? So this would be 1 over 2, this would be 1 over 4, this would be 1 over 8, and this would be 1 over 16. That makes sense? Right, okay. So that means this guy here would hold a weight of what? 0.5. This guy over here would hold a weight of what? 0.25. This right here would hold a weight of 1/2 of this. What's that? 175? I thought it was 165. Huh? Yeah. And this will hold a weight of what? 1/2 of that. Huh? 0.0625, right? So what you do is same way we did here, we took the 1 and we double it. What we do here is we take the number every time and do what? Half it. Okay, you understand that? So what would be the weight of the number? Well, I would add what? I would add 8. I would add 2. I'd add 1. Then I'd add what? I'd add 0.25, because that's got a 0. We skip over that, it's got a 0. We'd skip over this and we'd add what? 0.0625. And then that would be the decimal weight of that number. What's that?
11.3125.
Are you okay? Now this is where we get into problems, because if I wanted to represent a number like 2.6, we got problems. Why? Because the best I got is 0.5, and then I would start going, that's too big, right? You understand? And I would keep going down and down and down, and we can get into a long fraction right off the bat. So we limit our fractions. In fact, on tests and stuff like that, we're not going to have any fractions because how difficult they are to deal with. When the P8 processor came out, this was a microprocessor they put out, and it had problems with math, but it didn't have problems with the whole numbers. It had problems with what? Fractions. And they put that processor out, and all these physics instructors and everything got that and realized the thing did math wrong. And they sent it to Intel, and Intel said, well, we'll replace it for you, but you need to pack your processor up out of your computer and send it to us. And then we'll send you a replacement. And this got out on the internet, and it didn't take long for Intel just say, well, if you need a processor, just call us and we'll give you one, because this was so bad. But they had problems not with what? They had problems with fractions, because binary and fractions, we have a lot of problems with fractions representing very precise numbers. So these real numbers. So true story. P8, go back and read about it. Now we're up into what they call I5s and I7s, and they dropped the P designators. So guys, so y'all okay? Y'all feel comfortable with going from binary to decimal? So how do we go from decimal to binary? We need to be able to go both ways, besides using a calculator. Most calculators won't do fractions either, so you learn those techniques. That was really fun, learning how to write a machine language program, which is a binary program that handles fractions. And then you really learn about shifting over and making it a whole number and then doing it and shifting it back. It's really interesting to figure out how to do that. Okay, so let's say we'll start off with a little number, 163. So this is an odd number, so I should expect an odd binary answer. Now there's a couple ways we can do this. One way works with any base, and this is what the book teaches when you get your book. What they say to go from one base to the other base, what you do is you start dividing by the base you want to convert it into. So we want to convert this to binary, so I would come up here and I would divide this by 2. So now this is going to probably take a calculator, right? So what do we get? Y'all can use calculators if you want to, because I'm going to show you the way we can do this without calculator. What? 81.5. Well, what we do is we keep the whole number, and the technique is to keep the whole number and then multiply this by the base, and then that would be, and then all we do is write down the remainder. Of course, anybody knows that 0.5 times 2 is always going to be 1, right? You understand? So all I do is I'll bring down the 81, and I'm going to divide this by 2, and out here I'm going to put a 1. So anytime I have no remainder, I'll put a what? A 0. Anytime I have a 0.5 remainder, I'll put a 1. So now I got 81 divided by 2. What do we got?
40.5.
What's that?
40.5.
40.5. I'm going to write down a 1, and I'm going to bring down the 40. Okay, then I'm going to divide this by 2. What do I get? I get 20. I write down a 0. We didn't have a remainder. And then I would bring down the 20, and then I divide that by 2. What would that give me? 10, and I don't have a remainder. Right? I would bring down the 10. I would do what? Divide by 2. What does that give me? 5. I don't have a remainder. I would come down and take the 5, divide by 2. That would give me what? 2.5. Right? I write a 1, I bring down the 2, divide this by 2, and hopefully we better come up and get a what? A 1. And we get a what? We get a 1 with no remainder. Everybody okay? Huh? Now what we do is we let this thing fall this way right here. So the actual number would be 0, it would be this. Oh, I left out a 0, guys. So you let it fall to the left. So this up here is your what? This is your least significant bit. And then this down here is your what? Most significant bit. Oh, we didn't go far enough. Sorry. Got one more digit. So I write down a 0, right? Then I would do what? I'd bring down the 1, divide it by 2. And what does that give me? 0.5, and I write down a 1. So, sorry. So let me... What happened? I think I went to the wrong side. So our binary number would be this: 1 0 1 0 0 0 1 1. I stopped too soon. So we ended up with an odd number. How do I know it's odd? Because the least significant bit is set to a 1. Now let's verify our answer. How are we going to verify our answer? We'll go back to decimal, right? So I'm going to come up here and write down what? 1, 2, 4, 8, 16, 32, 64, 128. I'm going to add 128 plus what? 32 plus 3. Some of these guys you can do in your head, right? 2 plus 1 is what? Add that up. Hopefully it comes up and gives us 163. Huh? So we proved our answer. So what do? And this works with any base, but binary is pretty easy, because binary, you're either going to have an answer of 0.5 or you're going to have an answer, a remainder of 0. You get into base 16, your remainders are going to be real big, right? So there's got to be a better way.
So saying you get a remainder of 0.5, you put down the 1.
and write down the whole number. So notice here I had 81.5. So what did I bring down? I brought down the 81 and put a 1 on it and drop the remainder. So the technique is what you're supposed to do is you're supposed to bring this down, take this and multiply it times the base. So that'd be 2, because we're given a fractional remainder when actually what you're doing is you're writing down a whole number remainder, right? You understand? So when I divide by 2, I'm either going to get a remainder of 1, a whole number remainder of 1, or I'm going to get a whole number remainder of what? 0. Y'all understand what I'm saying? So if I was going to do this in elementary school and I had 5 divided by 2, what would you do? How would you write that down? 5 divided by 2. You'd say 2, and then you put your little r out there and put a what? A 1, which means you had a remainder of 1, right? But when we do math with a calculator, we don't get whole number remainders, we get fractional remainders. But that is the fraction of that right there. So the technique would be, if I get a remainder, if I want to find out what that whole number remainder is, I take what I divided by, and I multiply it by that fraction, and that gives me the whole number remainder. So that's actually what we're doing, but we're doing it in our head, right? So this is 81.5. Well, that's a 0.5. Well, that's 0.5 of 2. Well, what's 0.5 of 2? 1. So what we're doing here is anytime I get a 0.5, I'll write a 1 down. But in what we're actually doing is taking 0.5 and multiplying it by what? 2. And if you get into base 16, that's what you'll have to do. So if you get a remainder on doing this technique on base 16, is you divide by 16, and if you get a fractional remainder, you would multiply it by 16 and write down the whole number, right? You understand? And that way the number could be anywhere from 1 to F. So so when we get into bigger bases, we're not going to do this, because if we get into base 16, basically we use base 16 to represent binary numbers. So what I'm going to teach you how to do is I'm going to teach you how to go to decimal, but normally what we use hex for is to represent large binary numbers. So what you need to do is know how to go from binary to hex and hex to binary. Normally we do not go from hex to decimal. If I want to go from hex directly to decimal, by George, I'll pull out my phone and flip that sucker on scientific calculator, and I'll punch the number up and let my calculator do it for me. So that's what we use that's what in digital, that's what we use hexadecimal for, is to represent large binary numbers. And you'll find out once you learn the technique, you can fly between those two bases and you don't even hardly think about it. And you'll almost visualize a hexadecimal number as its binary equivalent, especially if it's small. So we need to find out an easier way. So the way we teach is we teach, and it's easy for me saying, okay, if I went from binary to decimal by using addition, it appears to me that I should be able to go from decimal to binary using subtraction. It's just logical, right? Because we're doing the opposite thing. So this will work, and if you want to use this, it's fine. And what you're going to say is, when we take our first test, you're not going to be able to use a calculator. So what you're going to do is you're going to prove to me that you can do these conversions without a calculator before you get the what? The right to use one. Because now you understand the base and you understand what you're doing. So let's find an easier way. This is the easier way to me. It might not be an easier way to you. So let's take the same number. $163. And everybody knows how to subtract. It's a little hard to divide, but 163. What I'm going to do is I'm going to start developing a table of the decimal equivalent of the powers of 2's. And I'm going to go 1, 2, 4, 8, 16, 32, 64, 128, and I always go one above what I need. Make sure I got another number of bits. Okay. And then I'm going to look, and what people try to do is they try to subtract this from that, but that's not what we're doing. This is the number, we're going to this. So what we're going to do is we're going to take this base 10 number, and we're going to look and see the biggest number down here I can subtract from 163. What's the biggest thing I can subtract from 153? 128. So I'm gonna put a 1, it's 163. So you're doing what the standard mistake people want to do is subtract this from that, but that's not what we're doing. We're subtracting this from that.
What's the correct
But you're guiding it backwards. I know there is not a 512 in 163. Okay. So when we did it, we added these together. So if you put a 1 right there and you started going back to decimal, you would add 512, right? You say, okay, there's not a, so what we're doing is we're not trying to figure out how many of these are in that. We're trying to figure out how many of these are in that. Okay, I understand it. But that's a standard mistake it makes, and so I'm glad that came up. Most people want to do what? They want to subtract this from that. But that's not what we're doing. We're subtracting this from that. So I'm saying, okay, the biggest thing I can subtract, how many 128, so we're saying how many 128s how many 512s do I have in 163? How many 512s do you have in 163? You don't have any of them. How many 128s do you have in 163? And by the way, you'll always have what? You'll either have one or you'll have none. If you say I have 2 of them, then you screwed up because there's no such thing as a 2 in the there's no such thing as the digit 2 in the binary number system. So I'm going to take 163 and I'm going to subtract 128 from that. Okay, we got 35. Can I subtract the 64 from 35? Can I subtract a 64 from 35? No. So what I write? 0. Can I subtract a 32? Okay, so what would I put? I'd put a 1 and I'd subtract 32. Okay, and that would come up and give me what? 3. Can I subtract a 16 from 3? No. Can I subtract 8? No. Can I subtract 4? Can I subtract a 2? Can I subtract a 1? Isn't that easier? Isn't that a lot easier than trying to divide? To me it is. All you got to do is just write down your chart, and then you can fly through these numbers as fast as I can put them up here. But
So it says if you want the preferred method you want to do.
whichever method is comfortable for you. Okay, that's what you're looking for. You're not looking for the way I like to do it. You're looking for the way it's easier for you without a calculator. You understand that? So that's what we're saying. So when we start off doing these bases, we're going to start off doing them without a calculator. And then on the next test, if half the class misses it, we're going to do the next test without calculators too. Eventually, if everybody starts getting all the numbers right, then we'll let y'all use calculators. But basically, I've never taught a class where we've been able to use calculators. But you'll be able to use the chart, right? I understand y'all have problems. And of course, if you dealt with the binary number system, the hexadecimal number system a lot, eventually you would throw that chart away, right? You understand? Because you start getting an understanding of the system and how it works, and you learn these powers of 2s when you get them. You know, I do all pretty good up to 2 to the 12th, but after that I started having a few problems. But it wouldn't take me long to pick that up, right? Y'all understand? Hexadecimal is a great numbering system, and all it deals with is just learning patterns. It's just like learning multiplication tables, and that's what you were doing when you learn multiplication tables. Is you did that so you wouldn't have to do all the adding, right? You understand? Let's do a little bigger number, and we're not going to do fractions. So let's say 2,632. So we should expect bit 0 to be a 0 because this is an even number, right? So everybody okay? What do? We start with the chart, right? Y'all got it. Most of y'all can do this in your head. So start off with what? 1, 2, 4, 8. A lot of people will write the chart down. 16, 32, 64, 128. 256, 512, 2024, 2048, and like I say, I like to go one pass. 4,196. Is that right? I might have messed up on. See, I even have problems like 1, 2, see. So what comes after 2048? 4,196. For some reason, I wanted to put a, and I can see that in my head. Should expect an even answer, an even binary number, right? By the way, if you get down to here and you hadn't run out of numbers, then you screwed up. So by the time you get to here, you should already be, this subtraction should either give you a 1 or it should give you a 0, right? You'll understand that. So if you're still subtracting when you hit that point right there, what does that mean? Yeah, you messed up. So we either get all the way down to here or we're going to run out of 1 somewhere up in here. But we'll never come down here and have like a 4. When I got down, subtracted 1 from 4. Yeah, starting with the most significant bit. By the way, when we do this, this number right here should always be a 1, right? What we got, Savannah? See how hard this is? So where did I lose you at? Right here? I thought that's what I had. And that's the problem we have when you start calling out these numbers. We have a tendency to get out of step, right? You understand? So if we come up here and we said 504, right now you might not understand it, but I could say 10100000100 and just call that out, and there probably wouldn't be anybody in the class that would get it right. I could come down here and say 504. How many could y'all write that down right? Everybody, right? Well, this is this same number in hexadecimal. You made a mistake. I don't hardly believe it.
No, I skipped the 64. So it's going to be.
I didn't do that.
1010001.
Wait. 101
001
1
100.
You did miss it.
Huh?
You hit 0 at 32.
Huh? So this would actually be 1 4. Say 1 2 3 4. 3 4. Is that right?
we got some big.
We got it. So I guess we need to do this, right? Okay, so what's the biggest thing I can subtract from over here? Let's put it over here so we got plenty of room. Biggest thing I can subtract is 2048, right?
2048. We got 584.
Are we okay so far?
Yeah. Then we
Can't do 1024. Can we do a 512?
yeah.
Okay, so I'll put a 1 down there. 512.
72.
72. Everybody okay so far? Okay. Can we do a 256? Can we do a 128? Can we do a 64? Okay. What's that give us?
80. 0.
So this will be a 0, 0, 1, 0, 0, 0. Now, if you watch what I'm doing, I'm going to come up here and I'm going to put a little dash here for every 4 bits.
Every 4. Okay.
Okay. And then I'm going to come down here and I'm going to write this down. And then I'm going to put a base 16. And this is what we're talking about. So if you had understood that and you'd say, Rich, it's A48. I mean, I could have got that just like that. But when you start saying 1, 0, 1, 0, 0, 1, 0, 0.
A represents what?
Huh?
A represents.
This is a base called base 16, but notice I did it in my head, right? You understand? And if I could get, if you understood going between hex and binary, if I was to call out the number A48, how many of y'all could have wrote that down right? Just A48. I mean, if I say A48, could you write that down? No, I'm just saying it. So that's what we're talking about, me conveying information to you. If I come up here and started saying 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and didn't have it on the board, how many would have wrote that down right? Nobody in the class, right? You understand? You say, what'd you say? What'd you say? If I'd have said A48, even though you don't understand it, could you write A48 down without making any mistakes?
Yeah.
Sure, right? And what I did, though, is I went from this to this without even thinking about it. This is a base called hexadecimal that we're going to talk about before long.
So how after?
Well, we're not in there yet.
Now, how we got simplifying 1000, then we do, how we did it like K48.
Wait, no, we'll talk about this. That's what we're looking. All we're trying to do is trying to figure out why do I need to know hexadecimal. In PLCs, you're going to learn 3 bases, and here in digital, we're more concerned with hex because digital is more oriented toward computers. Computers use basically they either convey information in binary, or they give it to you in hexadecimal, or they give it to you in a code. And what's a code? A code is when we use something to represent something. And so your computers have got to use codes all the time. Because on my computer, I've got keyboards F1, F2, F3, F4, all the way through F12. I've got 0 through this. I've got all this punctuation, all these letters, upper and lower case. And that has got to be represented in 1s and 0s. So how do they represent a Z? And when I press a Z key, what does the keyboard give? Well, it gives a code. It's a binary. It's a group of binary bits that when your processor or your program sees that, it interprets that as the letter what? Z. So we'll learn codes. The code we'll look at is a code called the ASCII code, which is still used a lot. Even on the internet, it's still used, even though they've expanded it. So when I look at the internet and I load in a web page, well, if you actually look at the source code for that, it's nothing but text. So when they send you a web page, all they're doing is sending your browser a bunch of text. And then it's just a bunch of what? Codes that tells your browser how to reassemble that page and put it up and display it. That's why, and it still pops up there. So you can look at a page on Chrome, and sometimes you can look on a page on Edge or one of that, and they basically appear a little different because the page is actually reassembled from what? From codes that's transferred. Now we use a code called Unicode. That, I'll show you all a little bit about that too. But what I was trying to get across is which one would be easier for me to convey to you and not make mistakes. Yeah, the A4A, right. It would be very hard for me to call this number out. It's even hard for you to look up here and do what? So I saw a bunch of y'all doing this, right? Trying to verify bit by bit. And so the binary number system, the longer the digits, the longer the numbers get, the more complicated it gets for us as humans to interpret it. So your computer is not going to use very little binary, even though it's a binary machine. What you have to understand is a computer runs programs to make things appear like that's not really what they are. So when I display this 0 here is nothing but a bunch of dots. That's all it is, that the computer turned on a bunch of dots. So it took this and interpreted it as what dots to turn on the screen to make it look like a Z, but it's a program you're seeing running. People don't understand exactly what's going on inside there, but I do. I mean, I've been in this guy's for a long time. I was in, when we did our programming in binary language, we called it machine language. That's the way I first learned processors, is binary language. That's before BASIC. BASIC was our first programming high-level language that came out. And then now, of course, we got all these other type of high-level languages that lets me write programs in English. But the computer don't understand English. So it's got to run through these translators and these compilers and all this other kind of stuff to translate what I'm trying to tell it into what it understands. Thank God for translators. So we don't hardly teach that. If you're working in PLCs, PLCs have been binary from the beginning. PLCs came out before personal computers were even a dream. We were still dealing with these, Radio Shack. First computers we got were put out by Radio Shack, Model 3s here. Radio Shack was one of the first ones to put a commercial, true desktop computer on the market. We had a bunch of toys out, the Coleco and the Commodore 64 and the TI 49A. Those are just toys. And then Radio Shack, believe it or not, put out the first desktop computer that I remember. And then, of course, now we carry more computer power on our belt or our pocket than was available on these computers. By the way, you ought to go in and start doing some research on the shuttle and look at the keypads up on the shuttle. Now, this was probably, and look at that is base 16. The keys are labeled 0 through F. So when they reprogrammed that computer, they did it in a binary language, which is pretty neat. Y'all watched The Martian? With yeah, but when he was looking at tables and he was keying in, redoing the program, and he was doing it in binary, it was a hex. The keyboard was laid out in hexadecimal, which is really on Mars. Yeah, that's a good movie. Kids don't like it because they like movies that start off with action in the first. They don't like movies that's got stories to them. I like it because he uses the ASCII code to first send messages back, which is pretty neat. And they got the ASCII code chart. So if you flip this thing around and you watch the movie The Martian, look at the chart that he uses to send. He uses the ASCII code to send it back. PLCs in computers, we don't deal much with this base, but a lot of y'all are in electronics PLCs. The AUT Intro to PLCs is one of your required classes. In the ILT program, the Intro to PLCs is one of your optional classes that you can take, and it's a really good class. If you're going to get into any type of industrial maintenance or anything like that, the predominant control device out there is PLCs. And the bases they use base 10, of course, for who? For us. And then they use octal, and they use hexadecimal. And all we're doing this is to enter very large deal with very large binary numbers. So we're still going to teach this, even though in digital computers it's not utilized too much. in digital computers, the two main bases they use, of course, they use binary, but when they display information to us, they're either going to do it in decimal or they're going to do it in hexadecimal. And that's what I was trying to bring up that while ago. So base 8. So base 8, we use the first 8 digits of the decimal numbering system. So I would write a number like 735. And of course, I'm going to subscript it to know, for you to know that is not a decimal number. So that is not 735. In fact, if you say 735, technically you're saying it wrong. We should say this 735. But once you get into it along and you understand this, most people deal with these numbers just like they do decimal. So what we do with this number is this would be 8 to the 0. So I'm gonna have to get this over to decimal, right? Because to me, I don't understand the weight of this number. Is decimal better? Is decimal a higher resolution numbering system? A higher resolution means we can represent bigger digits, bigger numbers with a smaller number of digits. And no, binary takes a lot of digits to represent numbers because we've only got how many combinations per digit? 2. How many would we have for decimal? 10, right? Base 8, we got how many? We got 8. So numbers in octal are going to appear bigger than they actually are. The decimal number will actually be what? Smaller than what we have written up here. This would be 8 to 0, this would be 8 to the first, and this would be 8 squared. So I'm going to get this to decimal. So what am I going to do? Well, what I'm going to do is just like we did before, but I'm going to write them down here. I'm going to put 7 times, and look at the chart and see what 8 squared is. Most people know what that is anyway. Yeah, 64. And then I'm going to say 3 times 8 to the first. What's that? 8. Right? And then I'm going to say 5 times 1. I'm going to do that math. So odds are you'll have to use a calculator here, right? Or do it in your head. You can do these in your head, but the more digits we add, the more complex it's going to get. So what do? We did the same thing we did in the binary number system, but the binary number system, we usually write it across the top. When we get into these bigger number systems, it's easier to drop the numbers down. So here's 735. Then I'm multiplying it by the what? By the decimal equivalent of these powers of 8. So what's 7 times 64? Should have a multiplication to 8 times. Isn't there an 8 times multiplication table on your chart there? It's supposed to be. Yes or no? I know there's a base 16. Okay, so y'all do this calculator. So 7 times 64 would be what? What's that? 3 times 8. And of course 5 times 1. This is an odd octal number. We should expect an odd decimal number. We should expect an odd binary number, right? You understand? Huh? I guess. And this is base 10. Now, how would we go from decimal to binary? This is where it starts getting complicated. This is where you're going to have a calculator. But if you're going to use a calculator, you might as well go ahead and buy a calculator that does the base conversion for you, right? You understand that? So normally we do not use the octal system to go between decimal and octal. And very seldom we use it to go from octal to decimal. We use this base to go from between binary. Now, how many combinations can this guy right here have? How many combinations can that have? It can have what? It can have 8. 0 through 7. So what we're trying to do is figure out how many bits of binary can have exactly 8 combinations. Now to calculate the number of combinations, All we do is take the base and then multiply it by some weight. Okay, y'all understand? So 2 to the 0 would be 1, right? So 2 to the 0, 2 to the 2, 2 to the first. So if I use one bit of binary, I can have what? 2 combinations. And what's the 2 combinations? 0 and 1. So we don't need that first one. So 2 bits of binary would give me 2 to the fourth would give me 4 combinations. That'd be 1, right? And that's all I can represent with 2 bits of binary. Y'all follow this. 2 to the third. How many combinations can I represent with 2 to the third? 8. What are they? 0, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8 combinations. How many combinations does each digit of octal have the ability to represent? 8. 3 digits of binary gives me 8 combinations. One digit of octal gives me 8 combinations. So what I'm going to do is I'm going to say a 7. So let's write the decimal equivalent over here. This would be what? 0, 1, 2, 3, 4, 5, 6, 7. What is this? A 7. What combination in binary represents a 7? 1, 1, 1. I'm going to write it down. 3. What combination represents a 3? By the way, you cannot drop zeros. I'm going to say 0, 1, 1. What combination represents a 5? Here's a 5. 1, 0, 1. Base 2. Convert that binary number over to decimal. I guarantee you it's going to be 747. Guarantee. Because all we've done is 7 combinations, 7 combinations, 7 combinations, 7 combinations, 7 combinations, 7 combinations, right? You understand? So if I can find a match between the number of combinations for a group of binary bits, then I can represent any base. But it's got to be a number, right? You understand? So I couldn't do this with a base 12. So if this was a base 12 and it wasn't a base 8, I couldn't go directly to binary because there's no group of binary that has exactly 12 combinations. Y'all understand that? Base 16 though. What's 2 to the 4th? 16. So what we're saying is if I've got a binary number, if I got a decimal number, any decimal number you could come up with, any decimal number you can come up with, I mean not decimal, any octal number you can come up with, 7, or let's do 3, 7, 4, 2, base 8. I could go what? 0, 1, 1, 1, 1, 1, 1, 0, 0, 1, 0, 1, 0, base 2. And I guarantee you if you converted this to decimal and converted to that decimal, you come up and get exactly the same answer. But which would be easier for me to give you? 3742 or 11111100 010? Hopefully you're going to say that. Okay, so let's say I had a binary number and I wanted to give it to you. And I wanted to come up here and give it to you without very little mistakes. Well, what I could do is I'm going to come up here and take a different color. And I'm going to come up here and I'm going to split this into groups of 3s. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And I'm going to figure this out. So what would this be right here? That would be a 4. This would be a what? A 5, a 5, a 2, a 5. This is base 8. I guarantee you if you punch these into your calculators, you're going to get exactly the same answer. Because what we're doing is we're using the exact number of combinations for 3 bits of binary. It gives us exactly 8 combinations. Each digit of octal has exactly what? 8 combinations. So what we can do is we can represent binary, octal with binary, or we can represent binary with octal. So normally we don't use octal to go between octal and decimal. We don't use octal to go from decimal. We use octal to go from octal to binary and binary to what? Octal. And it gives me the ability to convey very large numbers to you with very few mistakes. Now this was the first base that when the processors first came out, they were 8-bit microprocessors. And so when they started in PLCs, when they started figuring out, okay, what base, if they want to do this logic operation, instead of me entering all these ones, what would be a base to go to? PLCs originally used octal to represent large binary numbers. So we have all types of things in PLCs. We can compare, we can do logic, we can do ands, ors, which we're going to learn about. And I could do it with decimal, but decimal don't make any sense when you do an AND operation, because when you do an AND operation, you're dealing with what? If this and this is a 1, not if this is a 5 and this is a 7. Right? You understand? So computers, so when we enter these operations into the PLC, instead of using these binary numbers, what we would do is we would enter the numbers in what base? In octal. So every PLC that I know still supports the octal numbering system, even though most of your computers have moved to base 16 because it has better resolution, which means you can represent bigger numbers with fewer characters. And we'll look at base 16 in a minute. So this is why we learned the octal numbering system, not to be confusing. We use the octal numbering system not necessarily to go from to deal with base 10, but to make it easy to deal with what? To make it easy to deal with base 2. So I could take any number. I mean, any number. If I got a binary number, I do what? And you can't drop leading zeros. So you can't drop these zeros right there because that holds a weight, right? You understand? That holds a power of 2. You can drop zeros up here, but you can't drop zeros within the number. You have to write those patterns down. Everybody. So usually I don't drop any of them. So let's do this right here. Let's go like 3, 6. Now, there's no such thing as a 7 in an octal number system. I mean, there's no such thing as an 8 in an octal number system. So the biggest character, the biggest number you're going to have is what? 7. So this is base 8. Y'all convert that to binary for me. So I have a tendency to slant when I write. But all you got to do is learn 8 patterns. And it goes 1, 2. So now you're instead of dealing with 1, 2, 4, 8, 16, 32, you're dealing with what? 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4. Right? Now understand. 1, 2, 4, 1, 2, 4. So I can look at this and see this is a 3. 1, 2, right? I can look at this and see it's a what? A 7. And of course, after a while, what do? You literally learn the patterns. And once you learn the patterns, it's just like learning multiplication tables. When you multiply numbers now, you don't hardly even think about it. You know, if somebody says 5 times 3, you don't sit there and do what? Count 5 times 3 on your fingers. You know 5 times 3 is what? 15, because you memorize those tables. Those multiplication tables. Good gracious. They teach that in elementary school, right? What do y'all start off with? Flashcards? Y'all didn't use flashcards? Huh? That's your school? Me and math. I had problems with math all through school because math didn't make sense to me. And then when I got into the Navy and they put me in electricity and electronics, and you learned Ohm's law just brought light to my head. And after that, when I got into college, I aced every math I took after that because now math made sense because I saw the what? I saw the reason for it. I had one of my professors tried to talk me into majoring in math. Oh, okay. So let's get this and then we'll go. And let me make sure I got everybody that's here. In fact, the best thing to do is make sure, so let's go ahead and sign a roll.
You said this is recorded lecture.
Yes, recorded. Now I can't say when it's going to be up, because like I said, I got to go through a process to do it. So what I'm going to do is I'm going to turn my computer off, and it don't do anything when it's off, right? So it's got to be normally what I do on a class like this is I'll put, but it don't go to Blackboard, it goes up to YouTube, up to a private channel on YouTube. And then what I have to do is I have to go up to YouTube and then I have to link it into Blackboard. It's not done automatically anymore. So these lectures don't pop up instantly. Usually I do most of that on the weekend because it takes as long to or longer. So YouTube has a special format that they use. So they don't use a standard video format. So what do they have? What it has to do? So when you upload, it has to compile it over to a YouTube format. So there's a place that's a company called Real Player. Anybody got Real Player on their computer where you can download YouTube videos? And what do? They'll YouTube will change their format a little bit, and then you can't download anything, and then they figure it out, and then you can start downloading. So it's a real neat application, by the way, where you can download not only YouTube videos but a lot of videos. So we got it, guys. What we got? So this takes a little while. We're doing it in binary, so we got to. This will probably be easier for me to write it up here. So 3, 6, 2, 4. And I guarantee you, if you convert both these to decimal, they would be exactly the same thing. So once you learn this pattern, once you learn these patterns, you can go between octal and binary, or binary to octal, with basically hardly even thinking about it. Very, very few mistakes. So which would be easier, me giving you this one or you giving you that one? Yeah. So that's why these computers or these PLCs, when they start trying to convey binary information to you, then they're probably going to do it in another base besides what? Binary. And that's what a computer can do. A computer can make things appear like they're not really dealing with octal. A computer has no idea what decimal is. It can deal with BCD a little bit. Most of your processors can deal with something called binary coded decimal. Most of them can do BCD math, but for a long time they couldn't do any decimal math at all. So everything had to be what? Converted to binary. Then we'd do the math. Then we would convert it back into to codes where it would display decimal up here for us. It used to be real fun. Now it's not as challenging anymore because we got all these high-level language translators like C and stuff like that that lets us program in English and let it do it for us.
3, 36, 24, which is in
Octal.
octal, converted into
Binary.
binary.
Yeah. So notice this is the 3, this is the 6, this is the 2, and that's the 4. So if I was going to go from binary to octal, I would take my binary number starting at the least significant bit and split it up into groups of 3s. And of course in hexadecimal we're going to do exactly the same thing, but we're going to split it up in groups of 4s. And like I said, hexadecimal to me is easier because you're dealing with less numbers. But we still teach octal because PLCs still use octal. Most of your computers, when I figure out how to get to that information, when it starts information, these big binary numbers, it's going to use hex. They took away a lot of the stuff that we used to could do. I might do it on that computer right there. We could do memory dumps, and when it displays memory dumps, it's not going to display it in binary. It's going to do it in another base, right? Because memory dumps, you're dealing with actually 1s and 0s. Well, when the computer displays that, it knows that if it throws all these 1s and 0s, the programmers knew it, not the computer. The programmers knew if they start throwing all these ones and zeros on the screen, it would create more confusion. So what do? Well, they run it through a program that makes it display in another base. Like most predominant base now is in computers is hexadecimal. And PLCs are slowly moving that way, but they have a tendency of keeping older to support people who understand octal instead of trying to learn a new base. So PLCs will probably run the octal system as long as I'm around. So y'all learn something tonight?